You see this lock everywhere. This one.
You start? Okay.
It's a firestorm. So much food.
All right. Hello, everyone. My name is Andrew, and thank you all for coming to my PhD defense. This is the title of my dissertation, and it's quite a mouthful. And at times, it may seem somewhat discordant, but food safety is a pretty diverse sort of discipline, and a lot can happen from farm to fork. So there's three main areas that we're going to talk about. I'm going to briefly go through the first two, and I'm going to spend a lot more time on the last one. So we're just going to go through sort of sequentially what I've done. As a sort of disclaimer, at the heart of what I would like to do is to calculate something. And I like these sort of old Cold War examples of calculating things, where it's just you have a set of inputs and you try to determine what the output would be, and then you use that to make an inference. So this is what bomber aircraft crew would use, given what they're flying at and what the yield of nuclear ordnance was. They could calculate how big of a crater they would make. On a different end, for doctors, if they knew at what time the blast went off and what the current radiation dose was, they could predict what the radiation dose would be in the next coming hours, weeks, and days. But I like this sort of dial interpretation of it, whereas I'm just trying to see how things are related, and then I'm trying to use that in the future. And I'm probably going to reference these later. So for the first work that we did, again, the title is quite a mouthful, but I'm going to build this up incrementally to explain what we were able to do. So on the left are two different types of mold. There's Penicillium verrucosum, and in the middle there is Aspergillus ocratius, from which a chemical called ochratoxin A gets its name. Now, what's interesting is that both of these molds are capable of making ochratoxin A, yet they look quite different. And not only do they look quite different, they behave a little bit different, and they're found in different locations. So you can end up with having ochratoxin A in oats in high latitudes. You can have it in grapes in the Mediterranean. You can have it in coffee in the tropics. And for our case, it can also be found in pistachios. However, pistachios also have skins, and the skins cause interference with the assay that measures ochratoxin A. The way that the assay works is that it exploits this protein called an antibody. And what happens is at the tips, there are these highly variable regions. And through all of that variability, it can get exploited so that way you can make a specific sort of pocket for a specific analyte of interest. And then you could add on and you could continue doing your assay afterwards. Unfortunately, the pockets aren't as specific as the manufacturers would like. And it turns out that phenolic compounds can also bind into the pockets that were intended for ochratoxin A. Now, the way around this was we can use a fining reagent, which is commonly used for clarifying apple juice, because it's removing the phenolic compounds which were contributing to that cloudiness. So a little bit more formally, we're going to talk about, it's the structure of ochratoxin A that we're interested in, and we're using in ELISA kits where they're doing high throughput screening. That's the problem where we started to get these false positives from pistachios, because it turns out that prior work, we had these two phenolic compounds were known to interfere with the test. And what we're going to do is we're going to modify the protocol. We're going to add in a phenol absorbent called PVPP. That was the very long word at the beginning. So just very briefly, the first thing that we did was we found that as you increase the concentration of PVPP, it makes the resulting amount in fixed solutions goes down. We reduce the amount of phenolic compounds. However, we aren't really messing with the ochratoxin A concentration, which is what we wanted, right? We wanted a way of removing the phenolic compounds for this test. Once that was done, we then used ground pistachio skins as a sort of test matrix, and then we evaluated adding PVPP into the protocol in order to see if the cross-reactivity would go down. So what happens is, in black, the more of this phenol absorbent we add, the less of the phenolic compounds end up in the resulting mixture. Now, in white is the sort of degree of interaction. So you can see right at 0, it's just pistachio skins, but the test is reporting back that there's around 16 nanograms per gram of ochratoxin A. But that's the sort of false positive, right? So as we add more, it ends up with, we can get the cross-reactivity gets to go down. So hopefully that would work. We also measured color loss because there was a measure of the anthocyanins that were remaining. So just sort of in conclusion, it's just a straightforward addition. PVPP is that it's insoluble, so it can settle out of solution. And it can remove the compounds which were causing that interference. And since it's that simple modification, hopefully that would mean that it could be adopted in practice, right? Because they wouldn't have to change too much. As an aside, pistachio skins are sort of a worst case example. Maybe for other foods, you wouldn't need to use as much as we were using, but hopefully you could use the same setup of testing a range of PVPP concentrations and seeing how much you would need to make your cross-reactivity go down. Now for the next one, we were more interested in the interplay between hand washing and glove use. So people don't always wash their hands, right? And that's desperately concerning in a food service environment where they're touching the food that we end up eating. Now, there's a lot of sort of things at play. People don't quite know, how long with using soap is necessary. And then even if you do all of that, people may or may not even follow those instructions, right? So the alternative ends up being, well, let's talk about glove use. So maybe we can counteract that by making people wear gloves. But even on the glove use side, there is still sort of unknowns. Maybe if your hands are still dirty, maybe you're still transferring bacteria to the outside of the glove surfaces and you're still contaminating it. Or maybe the bacteria are permeable to the glove. Or, you're still interested, maybe the gloves give you that false sense of security and you're dicing around and you're moving through things and you keep your gloves on for your whole shift, and that doesn't really make a difference either. So what we're trying to do is we're trying to understand both hand washing and glove use in combination. Now, in order to do that, we were using an organism called Enterobacter aerogenes from Rutgers. And what's interesting about it is that it turns out that it has the same attachment characteristics as Salmonella. But as a surrogate, it means that we get to inoculate the hands of undergraduates when we do our experiment, and we don't really have to worry about them getting sick, but we can still study what the system is doing. So we inoculate their hands with a very high dose, right, 9 log CFU of this bacterium. And then we did 3 different hand washing scenarios, right? Just rinsing, kind of entertaining the idea of soap briefly, and then the full-on compliant hand washing for the whole duration. After that point, participants either dice a tomato with or without gloves. And once that was done, we measured how much bacteria was on the tomato samples, how much was remaining on participants' hands, how much was measured on outside glove surfaces. And we tried to understand how that worked in combination. So with a high bacterial load, it ended up being that when we measured the amount on participants' hands, regardless of hand washing, there was still the same total amount left. And that kind of has to do with the fact that it was a very heavy bacterial load. However, there were a couple of interesting differences that we ended up seeing. For one, the increased hand washing duration does decrease the incidence of detecting bacteria on the outside glove surfaces. And then for another one, when we're dealing with bare hands, the amount that gets transferred to the tomato you end up having less with greater hand washing duration. However, it's subtle. So in order to sort of visualize that, you can see on the bottom we had the amount of bacteria, and what we were using was cumulative probabilities. Now, that may be more relatable in terms of standardized tests, right? You take the GRE score, and you score in the 85th percentile. And what does that mean, right? Out of all of the scores, you scored higher than 85% of them, right? And then that knowledge gets used on whether or not you get accepted into grad school, I don't know. But what we're trying to do here is we're ordering the data, and then we're sort of seeing the slight difference between the hand washing treatments, right? So half the time, if it's just rinsing, it's in excess of 6 logs, whereas half the time, if it's the non-compliant, 5.5, half the time. For just compliant hand washing, it's under 5. So there is a sort of difference. It's subtle, and the way to sort of visualize and understand it would involve ordering the data. And this figure is going to get referenced a couple of times, just the notion of trying to order the data and understand about the system that way. Right. So in conclusion, right, you need both the hand washing and the glove use together, right? Because glove use did make a large difference in the amount that got transferred to the actual food. It was a very good barrier. However, you still need to have hand washing because it meant less got transferred to exterior glove surfaces. And also, just as an aside, we're going to talk a little bit more about ordering data. Okay, So this is going to be the last section, and it's going to take a while. It's going to involve 2 separate chapters. What we're going to be interested in is we're going to do forecasting fungal inoculum under climate change. But before I do that, I need to talk a little bit about probability. From here on out, I'm going to use something called Bayes' rule because I'm interested in different parameter values given the data that I have back. And this is how you end up solving for it in a probabilistic sort of manner, right? Because we're interested, right? Maybe it's a slope for the dial on how the relationships are. They're related by a slope. So given our data, what are the different possible slopes that we could use? And it ends up being a distribution. And I'm not going to get too deep into this, hopefully, because most of this gets solved by using a computer, right? It's like having extra computational power. So you should let computers do the things that computers are good at, and then we spend our time sort of specifying the equations that end up happening. Now, a little bit more of a hopefully relatable option to probability, I like using roulette, right? And I like roulette because it ends up where the payout is in proportional to the likelihood of the event, right? And I'm going to end up reporting for this first paper my results in odds, right? So if I guess that it's red, and then I get a 2-to-1 payout because I had a roughly 50% chance of happening. Or if I guess if it's between 1 and 12, I get 3-to-1, and a third of the chance of happening. Now, a little bit more abstractly, the problem that I'm ending up doing is that I'm setting up a roulette board using my data, but I want to see if there are differences between groups. And I'm setting it up that way. So maybe it might end up being that something, if it's red, has different chances than something whether or not it's black. And this is the sort of framework that I'm going to try to reference in the future. It's just, I'm trying to figure out, using my data, to figure out what these odds ends up being. Okay, so for the actual problem at hand that we're going to talk about, there is a disease of wheat called Fusarium head blight. You can see it affecting wheat kernels here. It's a particularly bad one because you end up seeing very large orange spore masses as well. Now, as a result of this disease, the grains become contaminated with a chemical colloquially referred to as vomitoxin. And I will leave it as an exercise for the student to guess what that does. But the thing is that this causes economic damage because growers cannot sell their grain if it exceeds, right, the regulatory amount of vomitoxin present in the grain. And there are regulatory limits for vomitoxin in the grain because grains become, right, food, bread, all of that. We don't want vomitoxin in the food supply. Now, one of the main causal organisms of this is Fusarium graminearum, which makes these fascinating structures called perithecia, which are essentially fungal cannons. And what they do is they forcibly eject spores at rates of 800,000 G. That way they can make it into the wheat canopy. Now the thing is that the rate at which these fire off, the rate at which they're made, and the rate at which they mature increases with relative humidity and temperature. But even if it's hot and humid and they just fire indiscriminately, it still may not be successful. They also have to fire at a period of time when the wheat plant is vulnerable. That ends up being during flowering. So this disease is favored by the combination of hot and humid conditions during flowering. Now, the thing is that this is somewhat of a common disease, especially right in the Midwest where you get rainfall during times when it's flowering. However, where we're standing right now, this disease is quite rare, primarily because conditions are too dry during the flowering of wheat. However, we all hear about climate change, so the point of the inference here is, would we have to worry about this disease in the future? Should we be worried about grains becoming contaminated with vomitoxin in the future under climate change? Because currently the climate may be keeping it at bay, and that might change in the future. Now, to go about doing that, we would like to determine how much of the inoculum source is present. Now, Fusarium graminearum is not present in this region, and one of the common reasons I get told for that is because there is no corn. However, there is a separate organism called Fusarium culmorum, and they make structures called chlamydospores, which are long-term survival structures that happen in the soil. And they allow this fungus to exist in agricultural soil on the timeline scale of decades. And this sort of organism is known to be around in this region, and it also can potentially make vomitoxin. And you can see what commonly back in the 60s and the 70s, Fusarium culmorum caused quite a problem from Fusarium root rot. because it's Fusarium culmorum, and it's infecting the culms. But anyway, it ends up being, right? So this is a potential inoculum source in the region capable of producing vomitoxin. So what we're interested in is we're interested in how much of this is out there, and is that related, and how is that related to the weather of where I looked and when I looked in time. So stated a little bit more formally, right, we're interested in Fusarium head blight, and ends up being deoxynivalenol is the formal name of the compound that we're interested in. As you can see, mostly in the Northwest, there's very low incidence of grains being contaminated by DON. Right? And we want to understand the inoculum source, and then we want to be able to do, essentially like I showed at the beginning, we want to make some kind of system with the weather so that way we could sort of forecast what would happen in the future. Now, in order to do that, what we did was we sampled from 9 agricultural fields across the region, from all the way from La Crosse, Washington to Troy, Idaho, and essentially let Mother Nature do the treatments because this is a precipitation gradient from decreasing to increasing precipitation. Now, not only did we sample spatially, but we also sampled over time every 3 months. So we get the amount that's back, and we want to understand how it's different based on where I look, and how it's different based on when. So within each field, there was a sampling grid of 9 1-acre quadrants in a little 3x3 grid pattern. And what we did was we took the soil back, we diluted it, and we plated it. And then we ended the final result after the identification procedure was that we get a count. So out of total soil fusaria on a plate, how many of those are Fusarium culmorum? Now, over the course of 2 years of sampling, you end up collecting and processing a lot. But what we're interested in is, right, if there's a greater proportion or not between fields. Now, this is where things start getting a little tricky, but we have the original data set, right? So I have counts and I have out of the total, but I also have what field it came from, I have where in the field it came from, and I have when. And what we're interested in is we're interested in modeling it as a proportion, right? Out of total soil fusaria, what is the proportion? Use a binomial distribution to do that. Proportions are limited between 0 and 1, so that's why this logit part is there. And what we end up doing is I'm essentially setting up my roulette board, is what's happening here. So I'm saying that while it is incredibly variable, I'm saying that the unique one I see is some sort of function of just an overall average proportion, and then maybe there's a different effect for each field, where in the field, and when. And I'm setting it up this way, and I'm using my data to see whether or not there are increased or decreased odds based on, right, field, where in the field, and when. I'm doing this mostly to understand the sources of the variability. Is it greater within a field or across a field? As an aside, when I was writing this, I also reached out to an Australian plant pathologist, and he had similar count data in grains in Eastern Australia. And that also is a place that undergoes a precipitation gradient. And he was kind enough to give me his data, and that's it on the other side. Now, doing the varying intercepts all part was nice about understanding where the data came from, but we're mostly interested, right, in understanding how things are related. So we would like to do some kind of slope. So the simplest thing I thought to do was you could go on in and you could do annual climate summaries for sort of like total rainfall, total potential evapotranspiration, like dryness, or total growing degree days, which would be like heat. And what you do, right, is we're interested in what the slope would be, and we're setting it up this way. Now, during review, it ended up that I needed to do a lot more complexity. I needed to test a lot more equations. This part was just because they were interested in not having straight lines. What if the line wasn't straight? What if it was curved? Polynomial regression is a way to do that. Now, I was originally doing these all independently, and I was asked, why were you doing independently? Why don't you add them in together in the same equation? And I didn't really want to do that because it ends up that my variables are correlated together, and that causes issues. So, right, for where we are, it's drier where there's less rainfall, it's warmer where there's less rainfall, and it's drier where it's warmer. And similar for Australia, it's warmer where there's less rainfall. Now, I'm a big proponent of using computers, but unfortunately, they take your instruction set quite literally. So when you're saying that you have two separate things, it's sort of saying that they're kind of, right, independent. And we know how to interpret these, right? Like what's the effect of rainfall, assuming that, the other variable stays constant. Now, another way of thinking about this is how much information do I gain knowing rainfall after I already know about dryness? And since they're correlated, the answer ends up being close to zero. It's because it's using the same information and it kind of breaks down. And that's going to come into play towards the end. A little bit more specifically for what am I doing, I'm using a package in R in order to specify the model equations that I'm going to show. And what it does is it interfaces with Stan, which is a programming language, and that's the one that's actually doing the brute force calculations. And the way they're doing that is they're actually running a physics simulation, which is kind of nifty. But the result is that you get, for say like a slope, like I showed before, you would get a long column of slope values, and their frequency is proportional to the relative plausibility given the data and given the model equation. And that's nice because then I have a whole distribution to work with. I can carry that forward and when I make predictions, and I can keep on with uncertainty. Now, the first thing that ended up happening was I just tried to see how good does my roulette board fit the data that I observed. So, right, I had 9 fields. There was 8 sampling points, right? 9 spots within each field. The cross is the actual empirical count that I observed. In gray, I sampled from the posterior distribution, and I saw what the predicted counts ended up being. And you can see for the most part, it ends up matching because there were so many options on the roulette board, essentially. However, there are still cases where there are high counts that aren't getting matched, and that's the phenomenon, just for a sort of jargony word, is multidimensional shrinkage. What's happening is that it's pooling all of the information together, and given that there's so many low counts, it's skeptical of predicting counts that are high. But it's fitting what I'm giving it, and I'm trying, and this is just sort of doing that. Now, the actual part that we were interested in, right, is seeing whether or not the odds were different by the different fields. Now, these are log odds, and 0 is 50-50, so that's even odds. Positive is more likely, negative is less likely. Nice part about doing log odds is most of it stays between 4 and negative 1. So you can see for these fields, right, field 1, 3, 4, and 5 have increased odds of me isolating Fusarium comorum from that field, whereas other fields out here have decreased, right, odds of doing it. Now, originally, I just started to plot those against the annual climate terms and see if there was a relationship, right? So maybe there is one, right? So where it's drier, there is a decreased, right, odds of detecting it, whereas where it's sort of less dry, you end up with other things. Increased odds, I'm sorry. So this is what sort of motivated me to move forward and actually do a slope, right? Maybe I could fit something in there for that term, and then I could use that to try to predict what it would be. As an aside, we also had each unique sampling quadrant, and we could look at those. Now, most of them did not provide any more increase or decrease to the odds. However, there were 26 where 95% of the time it excluded 0, and I'm plotting them here, ones which had increased odds and decreased odds. Now, what's interesting is that all of the ones where there was a decreased odds in isolating Fusarium comorum, they all occurred at the higher points within the field. And that's sort of known because yields are also lower up there. It gets drier up there quicker. That's what's getting observed. That's a nice little aside just from mining through everything that happened. Now, this is the part that I have to apologize for because I had all of these equations and I had all of these terms and they all seemed to be okay, but it didn't make sense to me either. And it still doesn't make sense afterwards. But what I'm doing is each line is a trend. So say for dryness, there's a decreasing trend as it gets more dry, right? However, there is still residual uncertainty. So that's why I'm plotting 100 samples. So even though you might have a consistent trend, there is still too much residual uncertainty. And because we're dealing with things that are correlated very high together, you end up, it gets very sensitive based on what's happening. It's almost like it's nonsense. But the thing is that I'm trying to do is that even though we're adding complexity, it's not helping. It's fundamentally, it's kind of limited. And this isn't of use to growers. And that was the problem that I ended up having. So just sort of in conclusion for this one is just right. There's nothing stopping anyone here from doing a similar approach where you have different experimental units in your data and you're trying to see where the variability comes from. For me, isolation frequency was more, even though it was quite noisy, it was still more variable across fields than the noise that I saw within the field. Also, just using annual timescales was too coarse of a resolution as a predictor variable. That wasn't useful. You need to be on a shorter timescale. You need more information than just what the fungal counts are, and you need a different framework to actually relate these fungal populations to what's happening. Now that's what we're going to do for the last part. I'm going to supplement the fungal count data with the dilution factor I used during plating. And then I'm going to try to demonstrate a different sort of framework for how I was able to relate all of this together. Okay, so we're trying to bring it all home with the last one. But before I do that, I'm going to do a little bit of an aside in hopes that it will make my data a little bit more interpretable. This is a map from World War I of the Battle of the Somme during 1916. Each small grid has a side length of around 80 meters, so it's about the area of a football field. The number within each one is the amount of British casualties which were sustained during the year of 1916. Now it's highly variable, right? You can have none to 20, to sometimes in excess of 700. Now, what if, out of morbid curiosity, I wanted to create more maps like this? What if I wanted to use the information within this map in order to map someplace that I haven't sampled from? I think that's a common sort of issue in science, right? You want to generalize to the population. Now, how can I make more maps like this? What would be a sort of simple way of doing that? Well, we could take the idea from the hand washing study, we can order the data, and we can start to see how that ends up working and see if we can gain any more insight from that. So this is the entire map. It doesn't take too much to add in that into Excel, and we can order the data. However, we're ordering it in reverse, like flood data for a flow duration curve. So on the bottom is the fraction of the map that's exceeded, and on top is the casualties per 1.5 acres. And you can read this by saying that, look, only, right, 20% of the time, or 1 in 5, the amount is actually above 100, or 1 in 10 is above 200, approximately. Now, this has an average of 50, but I can't just keep making a map and just put 50s everywhere, because that neglects the variability that we see in this map. A different way around it is to use an exponential distribution. Now, what we can do with them is they have a rate parameter. We can set them to just 1 over the average that we end up seeing, so 1 over 50. And if I do that, it makes a pretty rough approximation to the sort of properties that I see in this map. So I should be able to randomly sample from this and make similar maps, right? So you can keep going and you can keep doing this way. However, this isn't very good, right? This is the simplest thing that I could do. And each spot doesn't carry any information, right? Because it's just randomly sampled from. So if I did it again, it would still look different. But they have a sort of, it's approximating what I end up seeing. So we can move on from this, and then we could try to think through things a little bit more clearly. And we can say that, well, if that's what it looks like with an expected value of 50, what would it look like for different expected values? Maybe in a town, we would expect that it would be 100. What would that look like? Maybe in a field, it's actually a lot less. What would that look like? And this is all just sort of simulating from it. Now, I know that this is different, right? But I'm trying to demonstrate that you should be able to think generatively about the data that you end up seeing, try to come up with the simplest sort of way of recreating it, and then testing those assumptions, and then you can incrementally move forward and get better and try to improve that way, instead of just throwing all the variables together, adding it all with polynomials. Like, just think about the system that generated your data. And maybe we could go back, and maybe we can classify the original map cells on whether or not they're a town or not, and then maybe we can see on whether or not their rate parameter would be different. We're not. This ends here. But this is just a sort of case of me trying to explain, right, the process of generating this data. Now, I'm showing that because of all the things I've seen, that's very close to what fungal soil populations in agricultural soil end up looking like. So remember, it was a 3x3 grid. We have 5 different fields. It's the same location, but it's changing in time. And just like before, not always is the same cell the one that's the highest. And these are propagules per gram soil. It's like a population density. However, there is additional information, right? So I should be able to do what I did before with the map and use an exponential distribution, right? But I have more information because each field should be unique. Like field 2 was consistently lower than other ones. There's a different signal also in there in that there's a seasonality. And that when I end up seeing the highest amounts end up being in the winter and the spring, I end up seeing lower amounts in the summer and fall. So just like with that town versus the field, maybe I could do something like that and I could change what the expected value would be. And that's what ends up happening. Now, I need to make a sort of weather variable for this to do. And what I'm going to use is I'm going to use essentially the last 90 days of rainfall minus the last 90 days of something called potential evapotranspiration, which is essentially negative rainfall. And it uses all the other information and it all gets pooled together into one term. And that's to use to sort of explain the seasonality, right? You have periods of time when you're in a surplus, when it's cool and wet. You have times of the year when you're in a deficit, when it's hot and dry. And that's what we're going to use to try to change what that expected value would be. And this is what ends up happening, just as a little bit more of a spoiler. This is for field 4, right? We have our prior 90-day difference. I'm going to call it an atmospheric water balance. And you can see that we have an expected value that we're plotting. And just like before, you can plot from the distribution and you can see that it gets a little bit more constrained. But for here, you're predicting that the expected value would be a lot higher in times when you have more of a surplus and a lot lower at times when you have a deficit. Now, instead of making a bunch of maps, instead what we can do is we could say, well, how does the proportion change in the field? So in our case, we could say, well, out of all of this, there's a median value, right? 530 propagules per gram. And we can look at each month and we can say that, okay, well, it turns out that in these winter months, right, 60 to 70% of the field would be above that median, whereas seasonally and sort of, right, in the fall, it ends up being lower. What we can do is we can use different data sets to do that. So you can use a climate change data set, so that way, you know, this is warming trend that continues through the end of century. And then like a Sharpie, we can just paint over with the historical baseline and we can look at where it's different, right? So we could say that for this field, maybe you might have a slight increase in the winter, but you're going to have more of a decrease during the summer and the fall months. And that's how it's going to change. Now, I just showed everything, so now we're going to go back. I'm going to explain how I was able to do it. So like before, right, this is just the similar varying intercepts part proof of concept. Just using those 9 values for a field, what are the likely rate parameters? And that's just as a sort of reference. The actual sort of equation that I'm using is just you have an intercept and a slope, and AWB is that atmospheric water balance that I just showed previously. Now, just like before, but just a little bit more complexity, is that we're assuming that there's a average effect and each field gets its own unique offset and it gets its own unique slope. And we're interested in how they're different across fields. And you can kind of see how well we do, but I'm going to have more examples of that coming up. Now, for the atmospheric water balance, right, I already explained what that was. Last 90 days rainfall minus last 90 days total evapotranspiration. It's similar to a drought index, but it's getting standardized a little bit differently. And I'm using this because it could be a proxy for what seasonal changes in soil moisture can be. And I'm using the last 90 days because it's the approximate length of time between sampling, but if for your own research needs, maybe you care about, you can change this. I have code, you could use it. Maybe if you care about shorter timescales. Now over here, right, there's a data set of sort of modeled soil moisture for each field that I collected from. That's in black. And then in red is the atmospheric water balance that I'm using as a proxy, right? Because the global climate models that I'm going to use don't have a column for soil moisture. I have to kind of derive one of them myself. And I'm using it. And what's nice about it is that I'm using everything that's available, but I'm not treating them independently. I'm combining all of the information into one term because I don't want to deal with these sort of multi-collinear problems with weather. Now, I'm also going to use global climate models to do it. And we're going to take 20, and for all of them, what we're going to do is we're going to calculate the exact same index, and just like I showed before, we're going to average it across all the months, and then we're going to visualize changes that way. So this is the map again, as I showed before, all 9 fields. And you can sort of see the differences that we end up observing right across there, right? The sharp cutoff after we get to field 7. Though field 7 was quite interesting because we saw high amounts in the summer months. Now, just like before when I showed the exceedance curve, right, for the battlefield, this is the similar way. So this is the same as what was shown previously, it's just ordered as a frequency of exceedance in black. It's the actual data that I observed. Now, both in red and green are the different model equations for me trying to see how well I'm fitting it. And you can kind of see what ends up happening. Red is just using it for the 9, that's why there's still that much uncertainty. There's a little bit more for the green because it's pooling information, but you're still seeing the sort of shrinkage effect where it gets sort of like knowing all of the other things, it gets skeptical of seeing those high amounts. So instead of, as I showed before, when there was just increased or decreased odds, now we can just report what the expected value would be for each field, right? And we also can show an average. And then loosely related, we could still talk about annual precipitation and annual potential evapotranspiration. And you can see there is a somewhat similar trend where these lower amounts ends up being where there's less rainfall and there's increased dryness. But I'm not using these in the equation, right? Because they didn't help me previously. I'm interested in just using the seasonal component. I'm letting the field still be different. I'm assigning that, I'm using my data to do that, but I'm not making a claim for long-term climate where that came from. Now for the actual seasonal effects, it ends up being different for each one, right? So you have some fields like 1, 2, and 5 where there isn't that much of a seasonal fluctuation in these soil populations. They're still staying the same. Whereas you have other ones like 3, 4, and 6 where you end up seeing a greater amount when there's the surplus, right? When it's cooler and wetter. And we're going to use these just like before, so that way we can kind of forecast what changes in the soil populations would be, right, for each field. So for the most part, especially the ones where they stay constant, they're still going to stay relatively similar in amount under climate change. However, it seems like the ones that definitely exhibit more of a fluctuation, there would be lower amounts in the summer and the fall. But there's not really an increase, right, in the winter, nor is there really like a longer period of it being favorability, right? So based on all of this inoculum source is still going to persist in the region through climate change. However, it would still be lower at a time when it would be flowering. Right? So putting that all together, it's a framework for, you can report things as a frequency of exceedance. You can still use data that's variable in this way. And then we can report to a grower how much of their fields is in excess of a particular amount. I did the median because it makes things easier between fields when I'm plotting. But you could, if there were thresholds available, you could use those when you communicate risk. And it seems that even under climate change, this fungus would still persist in the region over time, though if anything, it would go down in the summer and the fall. Now, a little bit, just to wrap it up for future directions, since we have all of this information, it would be good to sort of go through and calculate other things. The goal is that since you have all of this information, I just would like to make it interpretable. Since I already had scripts for downloading data by location, out of curiosity, you can just go to Orlando, like where Disney World is, and you can gather data for that. And instead of something like evapotranspiration, maybe we can calculate humisery, right? A kind of discomfort index. And maybe you can use that and you can plot all 20 miles like a hurricane forecast. And you can just say that, you know, maybe this would be more interpretable to people than just sort of what the numbers are. I don't know. If the trend ends up continuing, you may or may not be able to go to Disney World in peak season without getting heat stroke. But to we kind of see what's happening, it's just trying to use it to make it a little bit. You can also subset data based on growth development stages. So this is the next step, right? So Fusarium camorum would sort of stay somewhat similar if go down. The next sort of question is, well, would the climate conditions end up being favorable for this disease? And this is a framework for allowing to do it. And hopefully, instead of just using temperature, we could use more data from the literature to make more metrics, right? That actually could communicate risk. We can do things like what the spore cloud would be. We could do parameters for those fungal cannons. And maybe we could go forward, and this is for Pullman, Washington, right? Even in the future, the humidity is still too low to favor that disease. And that should be everything. Anyone have any questions?
questions from audience?
Yes, Dr. Wu.
Good job, Andrew. I just have a question about your hand washing study.
Yes.
I guess the question that I have, why did you end up picking tomatoes for that particular work?
Just a common sort of, it was just the food item that we were doing, and it was one where they got their hands all up in it, and we were just using the whole tomato in the stomach, or afterwards it was easy to sort of dilute it and end up getting the amount that came
So
back.
they didn't slice the tomatoes?
Well, they diced it all the way through.
Okay.
So it was kind of like maximum, like their hands were all getting up in there the whole
Okay.
time.
I guess the question that came to my mind is because the pH of tomato juice.
Mhm.
Do you know what the pH is for tomato juice?
Quite low, somewhat acidic.
Quite low. So I was just thinking, wouldn't it make more sense maybe to provide your human subjects with a variety of materials, let's say for Greek salad or some other
Mhm.
salad, with varying pHs, because I guess with a very low pH, there is a chance of some of those microbes, and I think you use Enterobacter,
Mhm.
and I don't know much about its, pH tolerance or resistance, but I was thinking maybe, using a variety of vegetables or fruits in your mixture would have made a bit more sense, but,
It does. Then you kind of get into the logistics of doing the whole thing. So it's kind of just
Right.
tricky to get that many students in the first place, and you had to do replicates, and it's like
Sure.
that would be wonderful to do, right? Because it should be different across different foods as well, and like that's just a way to keep doing it. And also, sort of another case was we did a very high load, and that ended up sort of causing some problems in retrospect because the higher the load ends up being the lower amount that gets transferred. And then during review, they were asked like, well, why didn't you do a lower load? It's like, well, we would have wanted to, but we're already fighting variability even at a higher load. If it's a lower one, then it's even noisier and it gets even more difficult to kind of see what the differences are. Even just for tomatoes, I had to order it to kind of start to see enough of the subtle differences.
And nobody said lower, medium, and high levels
They could as well.
among the reviewers, I guess.
Yeah, it was just, well, it was kind of just, why did you do the high? And it was kind of just logistically, you get a little bit more control over what the dosage was. But then you have the other problem of the transfer rates as well.
Thank you.
Yes, Dr. Christensen.
I didn't get you wash the detergent,
No, it's just was the regular just hand soap.
and so not this which contained one of these antibacterial.
It was like I don't remember exactly. I think it was just dial. It was like just from right.
But some of them,
Some of them do, right? And then you could also go back and you could do the same experiment again. And you could say, well, maybe if you just nuke it all down, and maybe it would be even better.
yeah, I have another question.
Yes.
When you look on this fusarium on the field,
Mm-hmm.
you was looking on particular species?
Yes, I was.
And did you see, other moths kind of growing on the plate? And
Well,
how
for
this is related to, some of them may behave completely different.
exactly. So that is the case, and so it was total Fusaria. It wasn't just everything. So I was already kind of selective on the media for that. However, I did see other species like Fusarium solani, and like they did have a different, just like you said, they had a different kind of seasonal effect as well. It was very sporadic when I did end up seeing those, because I could kind of start to identify them when I was going from the soil plate to PDA. Like you could start to see some of the other ones. It's mostly just Fusarium oxysporum is the main one, but there are other ones, and you're right. But they're not really. It's difficult to kind of understand them. And when I was reading the literature, other ecologists were saying that too, where it's like we do know that it changes, but it's kind of sporadic. We don't quite have a handle on it. Whereas Fusarium comorum was lucky as a kind of just a model organism because for one, it could potentially make vomitoxin. That's why we're interested in it. And then also it was stable in the soil. Like it kind of had this sort of similar kind of trend that we could see. There were other things too. It looked like it was sort of dying out recently in Europe and other places in there too. So even though it was 2 years, hopefully we could sort of catch it. But it was just, that's the part that they kept around. It would have been nice to sample other things like stubble or that, but this was a stable, like there was always soil out there for me to gather.
No more questions?
Well, thank you very much. And let's give him a hand one more time.